welcome everyone. I would like to welcome for this seminar Ian Spielman, who's going to be our speaker. So Ian is a NIST fellow in Maryland, and he's an experimentalist who works with cold atoms. And today he's going to present his work, rapidly expanding and contracting BEC rings with the ties to cold atom cosmology. So without any further delays, Ian, the floor is yours.
Okay. All right. Thank you very much. And I'm really happy to see such a good turnout for this presentation. Yeah, so I'm going to be telling you today about our most recent progress at looking at analogs to cosmology using two-dimensional Bose-Einstein condensates, specifically, as the title says, rapid expansion and contraction of these BECs. The people I'm acknowledging on this slide are a combination of projects that I supervise myself, and on the bottom, projects that are in collaboration with other senior investigators at the Joint Quantum Institute. Specifically today, I'll be talking about work done with Gretchen Campbell on the sodium erbium experiment. And the names listed here are the current team members, but I want to give credit to the past team as well, who did most of the work for the results I'll be presenting today. So the current team is Yanda, Tim, and Shovik, and recent alum who have graduated, mostly gone to industry, are Swarnoff and Monica. Madison is doing a postdoc at JQI, and Hector was a postdoc, and he's also in industry. So as I like to say, they're all making more money than us now. And this is actually pre-COVID picture of that team. Much of the work we've been doing has been in collaboration or a close partnership with Ted Jacobson.
Ian, the slides are not changing. Are you?
I'm on a slide that has pictures of people.
No people, just trees.
Okay. Thanks for letting me know. Yeah.
At least on my computer, just trees.
Yeah, I see the same. Yeah, just the first slide.
All right, so let me try a strategy where I just share the screen without not the application then. It's not what I wanted. Okay, I'm now to the slide I was on before. Do you see pictures of people?
Yes.
People.
Wonderful. Okay, yeah, so all of these recent projects have been in collaboration with Ted Jacobson. Pictured here, I like to think of him as our theory mastermind. And a great deal of the work is in collaboration with Steve Eckel, who's now a staff scientist at NIST. So with that said, the sort of opening question that we would like to ask in this context is, what kind of things can we learn about this sort of view of the early expanding universe as it transitions from then until now, using something that we actually have in the laboratory, which is a ring-shaped Bose-Einstein condensate. And I'd like to lead off this talk by saying it's fair to say that we have certain analogies between these two systems, but the field theory we study with our cold atom system doesn't have too much to do with the standard model in general. So there are certain analogies we can make, but by and large, we can't understand a great deal about the early universe with these experiments. And I think that that's going to be universally the case. All right, so with that said, I want to take sort of a experimental backdrop and give you a sense about how I think about organizing the kind of experiments we do. So if you think about engineering any kind of system, I think the most common paradigm would be going by the name of bottom-up engineering. And in the quantum sector, this is most clearly illustrated with superconducting qubits, where they're literally fabricated a chip using bottom-up fab techniques. And similarly, when we construct systems of atomic ions or now Rydberg atoms, you have a pretty good idea about where every single quantum degree of freedom is, and you're attempting to control these individual quanta as well as you can. But there's a second paradigm for engineering for quantum simulation, and I'm going to call that Hamiltonian engineering. And the basic concept is that we're going to build up the Hamiltonian using well-calibrated control techniques, but we're not going to individually tell the specific constituents of the system what they should be doing. I like to think about this as an analogy to coaching. We're going to set the rules of the game, and we're going to let our players, the quantum particles, play it out, and we'll see what happens as experimentalists. So in that setting of Hamiltonian engineering, broadly speaking, with neutral atoms, we have three ways that we can control the system. We can apply potentials, we can use Feshbach resonances to change the interactions, and we can add terms in the kinetic energy of the Hamiltonian, so generalized potentials, vector potentials, and spin orbit coupling, and so forth. In this talk, we're going to focus exclusively on using only the first of these control techniques, applying potentials. And the twist, of course, is we're going to have non-simply connected potentials, and we're going to be changing them dynamically in time. All right, so another piece of credit I need to give on this talk is how did we get into this business in the first place? It's not like I woke up one morning and said to Gretchen, let's do analog cosmology. What actually happened is at lunch in San Feliu, Spain in 2015, I was sitting with Jason Ho over the ill-advised glass of wine you can have there. And he said he had an impractical idea, which was to have an arbitrary curvilinear shape like this and to inflate it dynamically in time and ask what happens to a one-dimensional bosonic gas when this happens. And Jason was primarily interested in particle hole production. So if you inflate this quite rapidly, you can have causally disconnected regions leading to particle hole production. And as you're going to see, that's not what we did. We had a ring-shaped VEC, and that's not what we saw. And we'll get to particle hole production towards the end of the talk. So what did we do? So what I'm highlighting now is our first foray into this direction, which is expanding of ring-shaped Bose-condensates. So what the top picture shows is a nice frame series that Steve Eckel put together, showing our initial Bose-condensate staying constant in time, and then having its radius expand for some period of time before once again remaining constant in time. I actually like this picture because it shows a pathology of our first experiment that I'm just going to mention to you now and not bring back again, which is that although the red line is staying constant in radius starting here, in fact, you probably will notice that this ring is larger than the subsequent rings. So in this particular experiment, in addition to the inflationary aspect of it, radial excitations were created, and a significant fraction of our result was dedicated to understanding the impact of those radial excitations and their damping into the properties of this real Bose-Einstein condensate system. And this sort of comes back to what I said on my earlier slide. Some of what we do has analogies to cosmology, and some we doesn't. And the sort of exciting radial modes at best has loose analogy to cosmological physics. But when we look at other aspects of this, such as the oscillation frequency of phonons, we can clearly see the redshift phenomena where rapidly oscillating phonons at short time become slowly oscillating phonons at long time. And we're seeing three different times here for the inflation to begin. And on the left is representative actual data. And in a couple of slides, I'll walk you through how we obtain the data in the newer experiments. The central focus of this talk today will be something we observed and did not understand in our first publication. So in this sort of hypothetical experiment, plotted both by numerics and linearized dynamics, what we're looking at is the oscillation of a phonon mode in a ring-shaped BEC that expands in the gray shaded region. And I already mentioned to you the decrease in frequency associated with redshift, but a secondary effect is a decrease in amplitude. And part of that amplitude decrease comes from a term in the effective 1D equation of motion for the phonons, which goes by the name of Hubble friction. Now, this friction is a non-dissipative friction. And in the data set we had for the first paper, we could weakly constrain the value of the coefficient in front of this term to be about 0.55. Now, at the time, this was quite puzzling. We were expecting a value of 1. And within our statistical uncertainties, we, in fact, were not in agreement with that prediction. Subsequent theoretical analysis, both by a group out of Spain, as well as Steve and Ted, showed that actually our naive idea of it being 1 was invalid for the case of real three-dimensional condensates be caused to expand. And the actual number has to do with the inverse sum of trap frequencies. And this value of 0.55 is quite close to the value of 0.5 you might expect for a system that's harmonically confined both vertically and along the ring direction. All right, so we're going to have a look then experimentally in this talk about a much more careful determination of this Hubble friction coefficient. But the experiment that all those data was taken in is no more. So this is Avinash, who was then the senior graduate student, standing next to the disassembled Zeeman slower. And to understand the antiquity of the slower, you should know that Bill Phillips was actually the person who wound this slower. So it's that old. And it went through generations of postdocs, and the cable on the outside of this is welding cable that when some of these wires in the inside shorted one night, the enterprising postdocs wound around it, ran hundreds of amps through it to keep this beast running for another 10 years. Yeah, but that apparatus has been reborn, moving from NIST in Gaithersburg to the Joint Quantum Institute in College Park. So like a phoenix, it's come back online, and these are some very early pictures from that lab showing both relatively nice ring condensates with and without phonons. So that previous slide, as well as the one I'm showing now, are actually slides that I gave in 2019 at a meeting of the Royal Society. Hopefully some of you remember that, maybe not, but certainly some of you were there. And this is the last slide I had there, which were future opportunities that I thought would be things to study. And in the intervening years, progress has been made on these things. For example, I forgot the citation. So these data are from Marcus Oberthaler's group. And by carefully ramping in the vicinity of a Feshbach resonance, they were very clearly able to see the sort of particle hole production that's associated with inflationary cosmology. And they could also see some evidence for hyperbolic geometries as well. So that's super neat. And this connects nicely to earlier work of Cheng Chin's group, where they performed similar experiments in a more homogeneous system. And what I'll be talking about today is the other box from this slide, which is not only seeing hints of Hubble friction in expanding universes, but seeing Hubble anti-friction or amplification of modes in contracting ring-shaped BECs. And at the end of my talk today, I'm going to present some potential opportunities, vintage 2023, and maybe in 4 years, we'll see how that goes. All right, so with that said, I'd like to sort of take a technical detour and think about what are the tools we have to work with ring-shaped superfluids in the atomic Bose-condensate context. So for starters, this is a CAD drawing. This was made by Swaranov, depicting our new apparatus. So our system is now fed by a 2D mod, and we then capture the atoms and cool using conventional techniques in the science chamber over here. So there's nothing particularly innovative about this. It's much, much more compact than the previous experiment with that human-sized Zeeman slower you saw. So we start with a relatively hot sodium vapor. We use laser cooling techniques and followed by force evaporation. And as I indicated, all of this sort of real scientific action goes on in here in the red box, our science chamber. I'd like to now give you a sense of how it is that we make ring-shaped condensates. So firstly, this region here that I'm encircling with the purple dots, that is meant to be the inside of our science chamber. And we apply light along 2 axes to control these atoms. Horizontally, as I'll describe in a couple of slides, we create a sheet trap using a horizontally propagating Hermite-Gauss mode with a 0 here in the center of the mode. And we apply arbitrary potentials using a digital mirror device by projecting downwards onto the atoms. Let's see. All of these potentials are blue detuned, so we're capturing in the node here, and the atoms are repelled from the light we shine with the digital mirror device. First, thinking about the 2D confinement, we create the 2D confinement by carefully shaping an initially Gaussian mode. Along one direction, the direction that's going to be horizontal, we expand, I'm thinking backwards. The direction is going to be vertical. We expand the beam in the Fourier plane. And along the direction that it's going to be horizontal, we contract it in the Fourier plane giving a horizontally extended sheet of light at the atoms and a focused sheet of light vertically at the atoms. Now, the trick here is in the back plane, we have a phase plate that writes a pi phase shift only on half the atomic beam that produces a mode which at the focus is a reasonable approximation of a Hermite-Gauss mode, as I illustrated before. So this is then a mechanism by which we can take atoms and squeeze them into individual 2D sheets. Secondly, we apply arbitrary potentials in the vertical direction using the digital mirror device I mentioned before. The digital mirror device has two features which makes it extremely useful. The first one is, as I said, we can apply arbitrary potentials. Secondly, we can trigger the DMD and cause these potentials to change in a frame-wise manner in time. This particular DMD can be updated roughly every 100 microseconds or so. A second feature that we take advantage of in this experiment is that of half-toning. Namely, the digital mirror device can have pixels that are only on or off, but we have multiple pixels grouped together within a diffraction-limited spot, meaning that each of the point spread functions associated with these sources largely overlap, meaning that this half-toned image here would produce a smoothed image when projected onto the atoms. So altogether, then, we have a mechanism to create ring-shaped BECs whose nominal scale factor is on the tens of micrometers. And it's good to point out that numerous people now have made ring-shaped BECs, including at least one member of the audience. I don't know if anyone else in this list is in the audience. So wonderful. We have a ring-shaped BEC. The final tool that I'd like to highlight to you today is the capability to imprint phonon modes. So what we do is start with an isotropic potential, or more likely a potential that's slightly corrected using half-toning to produce a uniform atomic density. We then briefly change the potential to be higher on 2 points and lower on 2 points. This applies a phase pattern that would excite the Q equals 2 phonon mode. We then return the potential to the original potential and allow this phonon mode to oscillate as a function of time. So here is sort of a series of pictures that you might see with that behavior. I'm not sure how well that worked over Zoom, so let me just sort of play it. So you can see the phonon running around in the ring. One thing I'd like to point out about this is that we have created a collective excitation of our Bose condensate. And this collective excitation has thousands of quanta of phonons in it. So although I'm going to call it a phonon mode, it is not one phonon in the sense of a Bogoliubov description where you create one quasi-particle in the phonon mode. It's a great many phonons. Taking the kind of movie data I showed before, we can do a radial average and then plot the azimuthal density as a function of time. And you can sort of see then the standing wave that's initially created, oscillating up and down, coming back to itself pi out of phase, returning once again in pi out of phase, and so forth. So data like this is in fact the underlying data that the majority of our analysis is going to be performed on. So here is such an example that we can, for each one of those curves, fit it to a cosine and obtain the amplitude of this phonon mode as a function of time. Okay, the data we get out of that for any particular image or series of images is going to be the frequency of the oscillation, the decay rate, and because we know the radius of the ring, the speed of sound. All right. Lastly, the way the data that we are acquiring has been obtained is by absorption imaging. Everything I'm showing you today is going to be basically in situ, meaning that we didn't allow much time of flight to take place, and you can see that the images are representative of the density distributions. Whereas as this frame of images shows, if one had waited longer, instead you might have something more related to the momentum distribution. So again, what we do then is shine a beam of light on the atoms and simply measure the shadow that these atoms cast. All right. So moving on from that introduction, we're going to be thinking about expanding and contracting ring-shaped BECs. And this is this sort of beautiful artwork that one of our Joint Quantum Institute public affairs people made to sort of illustrate what this is for the casual observer. All right. So turning back to the original experiment that was led by Steve Eckel in our group, what we were actually aiming to see, based on our discussions with Jason Ho, is particle creation, which can, if you want, be depicted as a horizons effect, where regions of this ring become causally disconnected, acquire some phase difference, and when they recombine, this can be interpreted as a creation of phonon excitations. In this experiment, we actually did not see that. And towards the end of the talk, I'm going to get to why that is. So with that in mind, what we were wanting to see, let's now delve into the experiment and understand what we're doing here. So what we're looking at specifically are collective excitations in a expanding or contracting Bose gas. All of our data is going to look something like this. The density is going to be, in this case, atoms per square micrometer. We're going to describe the many-body wave function of the system in terms of a local density as well as a phase. In terms of our analysis pathway, what we will do is collect many images under any given configuration so that we can take them and obtain the difference density for any given image with respect to that average. So this then is delta n, representing the change in the system with respect to whatever perturbation we applied. And here you can see there's more density on this side than that side. This would be the lowest order phonon mode. Then we're going to describe this system using some kind of wave equation, and we're going to go into a bit of detail about what wave equation we need to look at. And then we plot data like I showed before, showing the ring down of whatever phonon mode was created. So this phonon mode is a boring phonon mode, no expansion took place, and what you see is it simply damps in time. Now these phonons are going to be used to be simulating quantum, to be a model for quantum fields in a cosmological setting, exploiting Unruh's analogy. All right, now even in the atomic physics context, we are by far not the only nor the first group to think about atoms as an analog to cosmological physics, and I'll have some historic examples here, and later on we might see some other ones. So probably one of the most well-publicized one are Jeff Steinhauer's experiments moving barriers inside one-dimensional or highly elongated condensates, giving analogies to black hole physics, to event horizons. The experiment I showed earlier from Marcus Oberthaler's group had an aspect which was similar to an early experiment from Cheng Chin's group, where the interaction strength in this case was quenched, creating particle-hole pairs that they interpreted as Sakharov oscillations. And then I'm sort of highlighting our early dynamics of the early universe. So here's sort of the cartoon representation of our system. We create an optical field, which is approximately represented by this blue topographical map. The idea then is that the ground state might be denoted by the red bar inside this. In fact, that's more like the chemical potential. A surprise to us is that the potential actually is quite harmonic near the minimum, even though we thought we had the resolution to print a flat bottom, and we'll see later how we actually have confirmed that that's the case. So then our quasi-1D universe is a toroidally shaped BEC in a blue Detuan potential. We then ramp the radius of this following an error function curve as a function of time. And then we're going to see what the fields inside this ring do as a function of time. So the idea is that the scalar fields like phonons are analogous to other scalar fields that might be living on space-time as the universe expands. One really key difference between what we do here and the dynamics of the early universe that I want to make sure that everyone has on your mind is that this is a force dynamics, meaning that we scripted what the radius of this ring is as a function of time, whereas whatever caused the inflation of the early universe, be it inflatons or whatever, it's self-driving expansion. And currently, our technology doesn't allow us to do that with the laboratory. So this is one of the many ways in which we don't capture all the physics associated with the inflationary epoch of the early universe. So I showed this slide before. We have density, difference density, and we see the phonon modes. So then what we do to characterize the data, as I hinted at before, is we model this phonon as a harmonic oscillator. So we take the wave equation, we specialize it to a single mode. That single mode evolves like a harmonic oscillator. This wave equation would predict no damping, but like any real system, these phonons damp. As a result of that, we include a phenomenological damping term in the wave equation. Now, the part of the audience actually reading the equation will notice the transition from the density variable to this chi variable. Chi is simply related to the difference in density, but it's also scaled by r to the power of alpha. And this power of alpha is actually key in our understanding why our previous description of Hubble friction was wrong. And it's also relevant to why the fact that our trap is harmonic also matters. So alpha is related to, in a power law potential, the inverse sum of the power law exponents, both along the z direction, which is extremely harmonic in our case, as well as the radial direction, which we would thought would be well modeled by quartic or higher order. Okay, and this gives the coefficient alpha that is used to ultimately give a convenient wave equation for our phase-like parameter chi. Here is our phenomenological damping term, but this is not the end of the story. There's one more term, and this is the Hubble friction term. So what Hubble friction is describing is velocity-dependent damping, and I've put here an arbitrary coefficient, but in fact, the theory cited down here predicts that this coefficient should be equal to this alpha. Keep that in mind. So we're going to treat it as an independent constant, and we're going to see how closely related to alpha it is. So for a long time, to me, Hubble friction was actually rather mysterious, but the effect is quite simple. So imagine that you have a harmonic oscillator, and I don't have a slide for this, unfortunately, so hopefully you can see me in a tiny window somewhere. As a harmonic oscillator oscillates back and forth, one can imagine changing the trap frequency. Okay, right. So where I left off, I think I was just commenting that the Hubble friction coefficient predicted by Steve and Ted's theory is going to be alpha. We have phenomenological damping. And lastly, in our analysis, when we perform fits, the frequency omega that this phonon oscillates at is of course related to the radius, just the speed of sound divided by the radius. And the overall scaling of this, when you account for the change in density as the cloud expands, also depends upon alpha. That's also going to be relevant moving forward. All right. So then, as you've sort of seen in data before, we start with small phonons like this and expand them like that, or in the new data set, also start with large phonons and contract them. The picture is similar to the earlier paper. We take data like this, and now the fit knows about the radius as a function of time during this expansion or contraction period, and we fit it to this model, which includes also the Hubble friction coefficient terms. All right, so in the previous paper, we had very nice agreement when one focused on all the terms for the redshift effect. So we were very confident about the redshift before, but as I indicated, we had high uncertainty on the Hubble friction term. And the reason we had the high uncertainty in the Hubble friction term is we had timed the expansion to be accidentally to be occurring at the phase of the oscillation when the Hubble friction has the least effect. That is, in my harmonic oscillator example, when you change the potential at the extrema of the motion, so the amplitude of the oscillation remains unchanged. All right. All right, so then now switching over to the new project, the goal is to simulate Hubble friction. And we're going to do everything we can to bring out this term in our data analysis and our selection of data acquisition. The very first difference between this project and the previous project is that we include both expansion and contraction of our rings. And this already will immediately show us the data that the expansion, as we saw before, attenuates fields, but contraction amplifies the fields. So this sort of drives home that this term, although it looks like it's going to be a friction term because it's sitting next to a first derivative, it is not really a friction term. So just to make clear then precisely what we're doing, we have our ring-shaped condensate. We have a azimuthal angle as well as a radius. We take differential data, as I mentioned before, such as this and this. We perform first a radial average to have the density only as a function of the angular variable. And then we assign a sinusoidal for the lowest phonon mode angular dependence to this mode and follow only the time evolution of the remaining amplitude term. And that's what's plotted in data such as this. The dots here are in fact measurements of the radius of the ring plotted along with our command from the digital mirror device. So this is working quite well. And in this case, we see an increase in frequency showing us that this was a contraction experiment. We then, knowing the radius, having a fit parameter alpha, we can convert from the density variable to the chi variable and fit to this equation for chi. Let's see. I think I've highlighted this before, but let's reemphasize it. So all the Hubble damping dynamics occurs while the expansion or contraction is taking place. There is slow damping, which we include phenomenologically, this occurring at all times, but in particular after the expansion or contraction. And as additional fit parameter, we have the alpha, which was living in the frequency. Okay, and I mentioned that the strength of the Hubble friction depends upon when you choose to expand or contract with respect to the phase of either the density or chi, take your pick. And this is the strongest or weakest when r dot over r is maximal or minimal, as you'd anticipate from the equation. So this can be depicted as on this graph, which is in these graphs, which is entirely a numerical simulation. This simulation, and this was done by Monica, what the simulation is showing is including damping what a representative experiment might observe. And we're particularly interested in the overall envelope function of the decay both before and after. And we're going to be looking at the extrapolated difference for when the size was at the point of maximum expansion rate, which we're going to be calling T peak. So as we move this forward in time, for this contraction experiment, what you're supposed to see is that the ratio between the initial and final amplitude is oscillating in time, or oscillating as a function of phi, which is oscillating in time. This is giving the information that there's a phase dependence. And the numerics plotted here were computed both with and without the Hubble friction term present. We can simply artificially remove it. And we see that with the Hubble friction term present, there's a decrease as given by this red curve of the change in this ratio. So that's going to be now specifically what we'd like to see in experiment. And here is that sector of the data. So we analyze the data in exactly the same way that I indicated that we were analyzing the simulation. And we're going to obtain the envelope and extrapolate it to its value at this time T peak. And we're going to plot the A final over A initial. The symbols are our measurements of what this ratio is. And the various curves are plots with different values of the Hubble friction. The blue one here is plotted for, I think, 0.3. One of the other ones is 0, and I don't have my speaker notes, so I don't actually remember which one is which, but I'm 95% sure that the dashed one is a Hubble friction dot dash of 1, and the dotted is 0. Okay, so this, and what this is showing you then is that in this contraction kind of thing where Hubble friction is supposed to provide an amplituary effect, we see some amplification, particularly in the smaller phases, but interestingly for larger phases, which correspond to larger decays and more initial, larger delays and more initial decay, the data is almost consistent with both the 0 Hubble friction as well as the small value. Okay. So in our final determination of the Hubble friction coefficients, we take a large number of data sets, such as depicted here. These correspond to different initial delays, both for contractions and expansions. And these initial delays serve to give us different phases for which the Hubble friction is active, as per the previous slide, giving both the largest and smallest effects. And in terms of data taking strategy, this is the biggest difference between the previous experiment, that we enabled our experiment to be tuned to be most sensitive to the Hubble friction. We then fit these data sets using a global fit, where each set, either the contractions or the expansions, had independent determinations of all the constants that I've mentioned, including the damping and the Hubble friction and the alpha coefficient. And the takeaway is here. The previous work, this is the original expanding ring experiment from our group, determined the Hubble coefficient to be 0.55, which is an extremely good agreement with 0.5, which would be what would be predicted for fully harmonic confinement. Both for the contractions and the expansions, our new data set has appreciably smaller uncertainties, and it lies just outside the single sigma error bar for the previous measurement, for two values which are not consistent with our trap parameters. So let's think about that. So again, here are the new measurements. For our determination of alpha, we find alpha very close to 0.5, consistent with our harmonic trap. And how is alpha determined? Well, alpha is determined by looking at the speed of sound as a function of time. And as the ring expands or contracts, the change in the speed of sound is dependent upon this alpha parameter. So alpha is consistent with half, which is vastly inconsistent with our observations. And here again are the two papers that give different variants of this kind of prediction. So with this, we're sort of moving now to the end of this presentation. Why is it that there can be such a large difference? Well, Zoran brought up one difference already, which is the expression giving rise to this definitely assumes Thomas Fermi, although it's dubious that in our regime this could give a factor of 2 difference. Secondly, we create very large amplitude phonon modes. So if you look at these data, for the vertical scale is the same, you can see that there are 50 atoms per square micron of density difference from 0 to here, comparable to 150 for the peak density. So these are extremely large phonons modes, and it's possible that we're entering into a regime where these are nonlinear. So it could be that this nonlinearity is changing the effects that are otherwise assumed for small amplitude phonon excitations. Another feature which I haven't mentioned is that as this phonon undergoes oscillation, it can in fact couple to radial degrees of freedom. And this was a significant parasite in our earlier experiment, where if we plotted the radius as a function of time, it did not perfectly track with what we commanded, and it underwent oscillations. We don't see anything like that in the present data, which is kind of a surprise to us. So it could be the radial degrees of freedom are also playing a role in addition to simply determining alpha. So I guess, so altogether, we've determined what the Hubble friction coefficient has to be with high accuracy, and we're left with a puzzle. We don't know why it differs by about a factor of 2 from what the Thomas Fermi calculations give us. All right, so sort of in the spirit of my early slides, I'd like to think about what kind of new opportunities we might have for the next couple of years. And I'm sort of giving some ideas that are inspired by other analog cosmology kind of experiments. So both of these are water body hydrodynamics. So a lot of what we've done so far has been very one-dimensional, as is similar for this sort of flow tank kind of experiment. And for example, Jeff Steinhauer's analog cosmology event horizon work is exactly in the spirit of this. But in our experiments, we obviously have two-dimensional systems, and I think we have some neat opportunities to continue this analog cosmology in the Bose gas in 2 dimensions. This is just a cartoon of a vortex I happened to have from the old days when I was making vortices, or even 3 dimensions, where we could basically poke a hole in the center of a 3D BEC and drain out atoms to have even closer analogies to 3-dimensional event horizon surfaces. So I think that these are some pretty neat directions we can be going, and just to sort of give indications, what we're considering pursuing in the laboratory right now is sort of close analogies to this 2-dimensional system with the drain hole and vorticity. And with that, I'd like to briefly conclude with what I call my shameless self-promotion slide, which has a bunch of other neat experiments that my group, both myself and in collaboration, have been working on. So with that, I'll go back to this, and thank you for your time.
Thank you, Ian. Sorry for the interruption in the middle.